Okay, so this example is going to be a really everyday life example. Why does dropping an ice cube into a glass of water cool it down? And what is the kind of the most important part of the cooling process? Um, so what we have here is 200 grams of water at 30 degrees Celsius, and you drop in 50 grams of ice at -5 degrees Celsius. What will the final temperature of the system be? And it says in the question that no energy is exchanged with the environment, which is cluing you into the fact that energy is conserved in this process, and the total sum of all the heat exchange has to be 0. Okay, so I'm going to use my flowchart method that I introduced in previous videos. And first, make note of my two initial states. So we've got, let's start with the water, because the water is going to be easier. The mass of water is 0.2 kilograms, and it is liquid water. Let's even just go ahead and call it liquid. And that is at 30 Celsius. Okay. And now that transforms into, now I'm going to assume that the water doesn't freeze when you drop an ice cube in it. I'm assuming that the ice cube is going to melt, which if that ends up not being the case, we'll get a strange answer that doesn't make any sense. So of course, this won't change the mass of what we have. It's going to remain as liquid, but the difference is it will reach final temperature. Let's just call it T, is the unknown final temperature, okay? And this process is going to have a Q associated with it. We'll call that Q1. And this, of course, is a temperature change, but not a phase change. So that's going to be an MC delta T type temperature change, type heat. Now, on the other end, we've got the ice. So here we have 0.05 kilograms of solid ice, which is at -5 Celsius. So now this one's going to be a more complicated transformation. The first thing that's going to happen to it, since ice melts at 0 degrees Celsius, that means the first thing that needs to happen here is the ice needs to warm up to the melting point. So in this step, it's going to remain as solid ice, but it's going to warm up to 0 degrees Celsius. And that is a temperature change, but not a phase change. So we'll call that Q2. And that's going to be an MC delta T type of heat. Then the next thing that's going to happen is we are going to go to a state where the ice now melts. So we have 0.05 kg of liquid water now. And again, don't forget, you can't change the temperature in that step because this one is a phase change only. So that'll be Q3, which is an ML transformation heat. And then finally, I'm kind of running out of space here, but maybe I can squeeze it in. Finally, we've got 0.05 kg of liquid water, which is going to be at final temperature T. And that is going to be a temperature change. So Q4 is once again going to be a MC delta T type of heating. Okay, and you'll notice, first of all, of course, I do what I described in the previous videos, the whole step-by-step process where I walk up to the melting point, then I melt, then I keep heating after that. But also, I just want to highlight for you, notice that the final states are the same. And that's the real key point for thermal equilibrium, that both of these systems are reaching the same final temperature. That's the key of the physics of the fact that this has reached thermal equilibrium. Both of them are at the same final T. Okay, so the next thing you would do is start calculating out all these Qs using the information that we learned previously. For Q1, again, this is an MC delta T type process like I wrote there. I'm just going to try to save some space here because I see I have a lot of stuff to calculate. So M is 0.2. I'm going to go ahead and drop the units and just use all SI at this point. C, I notice that I have liquid water here. So that means I want to use the C for liquid water. So that's 4186. And then delta T, I can see here in my chart, the final temperature is T. The initial temperature is 30. So I'll just write T minus 30. And note, by the way, the T I'm going to get is going to be in units of Celsius at the end of the day. Okay. So this has a variable in it, so you can do a little bit of math there if you like, but there's only so far we can simplify that at this moment. Q2, I see my mass here is 0.05 looking at my chart. My C, I want now the C for solid ice. That's given in the question as 2000 joules per kilogram Kelvin. And my delta T, I'm going to be going from 0 and coming from -5. So 0 minus a -5 or 0 plus 5. The delta T is plus 5. Okay. Then Q3 is a heat of transformation. First thing I should do is ask myself, should this be a positive or negative heat? Because I remember you have to put that negative sign in yourself. This should be a positive heat because the ice cube is absorbing energy from its environment. So this is a positive, and a mass is 0.05. And I want the L is going to be the heat of fusion. So I look up the heat of fusion up above there, which is 33.5 times 10 to the 4. And then let me see, can I squeeze Q4 in at the bottom? Q4 is an MC delta T. The M, once again, is 0.05. The C is going to be the C of ice. No, sorry, the C of water. Look, I have liquid water there. So that's going to be 4186. This is where the chart comes in handy. You can see it's pretty easy to get confused here. My final temperature is T. I'm looking here. And my initial temperature is 0. So T minus 0. And there's my 4 Q values. And then the last thing you would do is sum these 4 up and set it equal to 0, which is going to be a little bit of algebra. So I don't know if you want to see that. Maybe I'll try to go ahead and do it for those who want to keep watching the video. Hopefully I don't make any mistakes here. This is going to be a lot of algebra to do on the fly. So Q1 is going to be 837.2 T minus 25116. Q2, 0.05 times 2000 times 5 is 500. Q3 is 0.05 times 33.5 times 10 to the 4 is 16,750. By the way, just as a side note, notice heating the ice cube up by 5 degrees only took 500 joules. Melting it took 16,750 joules. That's why it's much, much more effective to put an ice cube in your drink than to put in like some cold water, because the melting process is going to absorb a lot of energy. It's not just the fact that the ice cube is cold that matters. It's actually the fact that it undergoes a phase change that actually absorbs a lot of the energy. Phase changes have quite significant energy changes associated with them. Usually, the energy from a phase change is much more than the energy from a temperature change. Okay, so there's all my Q values. So the next thing I would do is add them up. I'm going to need to make some space. Let's go ahead and delete the question. You know what the question is by now. this as well. Okay. So the next thing we do is we say that the sum of these four has to be 0. That is conservation of energy. All of the heat exchanged sums to 0. And naturally, some of these are going to be positive and some of these are going to be negative. It might not be quite obvious what's positive and what's negative for the ones that have variables in them, like Q1. But rest assured, Q1 must turn out to be negative if this makes any sense. Anyways, so we sum all these up. I'm not going to go ahead and copy all four. Let me see if I can do a little bit of algebra while I'm copying it down. Let's combine the t terms together. So 837.2 plus 209.3 gives you 1046.5 t. And if I combine all the constants together, 25116 negative plus 500 plus 16750 gives me negative 7866. And notice that the signs did work out, so that's a good sign, no pun intended, that I haven't made an algebra mistake, because I definitely don't have a negative sign mistake. At least I'm not going to get a negative temperature, which wouldn't be good, because a negative temperature would mean like you can't have liquid water at a negative temperature. Okay, so divide 1046.5, and I get T equals 7.52 degrees Celsius. And in these problems, you should always take a second at the end of the problem and ask if this makes sense. I should have been able to predict initially that if I am correct, number one, the temperature needs to be above 0 degrees Celsius, because I assumed that it was liquid water. So if it's going to be liquid water, it has to be at least 0 degrees Celsius. And then it better be below 30 degrees Celsius, because adding the ice cube can't heat up the water that was already warm. It's got to cool it down. So I was anticipating an answer between 0 degrees Celsius and 30 degrees Celsius. And in fact, that's exactly what I got. This seems plausible to me. Adding an ice cube to the drink cooled it down to a nice cool 7.5 degrees Celsius from 30 degrees Celsius. That is plausible. So that's how you handle these thermal equilibrium problems. If you try to do them by plugging numbers into formulas, you're done. There's no way you can keep track of all these numbers. There's way too many numbers, too many equations that are too similar to each other. But if you use my flowchart method to keep track of all your Q's, and then just keep in mind of summing them all and setting it equal to 0, it's a slow, laborious process, but it will systematically get you to the right answer eventually.